We talked last time about the normal curve, and I had a curve that looks something like this. Right, remember the mean was 110, and the standard deviation was 8, right? We use the 68, 95, 99.7 rule to kind of figure out questions like, okay, well, what if we wanted to figure out the probability that x is greater than 118? Well, 118 is a nice number because it's exactly one standard deviation away, right? So we can kind of shade this way. We would say, okay, well, you realize that this range in here is 68%, this is 16, this is 16, so the answer here is 0.16. The question we're going to look at right now is, what if I asked you the probability that x is greater than 119? Suddenly that's a whole different question, right? Because the problem is that 119 is right here. It's not exactly 1 or 2 or 3 sigmas away. It's, it's 1 point something sigmas away. So this becomes a much harder question. And actually, the 68, 95, 90.7 rule cannot be used for this question because you can only use this if it's exactly 1, 2, or 3 sigmas, which this one is not. So we have to do a whole different approach for a question like this. Even though these two questions look very similar, they're very different. So how would you do this question? So let me draw that picture again. It seems like for like the 10th time, but here we go. Okay, so mean is 110, sigma is 8, and we're asking the question, what is the probability that x is greater than 119? Again, not 1 sigma. So we think about it this way. Here's 119. Well, we are looking for this area, right? And it turns out this is a case where our calculator is really, really helpful because our calculator has a function called normal CDF, which we're going to get a lot of practice with in class. And the way normal CDF works is you give it a left number, a right number, a mean, and a standard deviation. So in this particular case, the left number, meaning the left boundary, normal CDF, is 119. The right boundary, remember the normal curve really kind of goes on forever, asymptotically approaching the axis but never touching it. So essentially, if you pick some number way, way, way out here, okay, that's big enough. So I'm just going to put some big number like, I don't know, 9999. Now what is the mean? 110. And what is the standard deviation? 8. When I do that on my calculator, I get 0.1303, which is the area under the curve. It's this area right here, up here, and that is the answer to that question. So a lot of questions involving normal curves can be used with this normal CDF. You could use normal CDF for problems involving exactly 1, 2, or 3 sigmas instead of the 68, 95, 90.7 rule, but there's no reason to do that. So let's just do maybe 2 or 3 examples of this, and that'll be kind of all we have to do. So using the same numbers as before, I'll draw it a little bit smaller this time. So 110 is the mean, equals standard deviation is 8. Okay, what if I asked you, find the probability that x is less than 95? And again, 95 is not exactly 1 or 2 or 3 sigmas. So here's 95, and we're looking for shading this area. So we use normal CDF. CDF, by the way, stands for, I should have mentioned that before, it stands for cumulative distribution function. So in this case, it goes left, right, mean, standard deviation. Left, there really isn't a left border, so we put some number that's basically way, way, way out here. You could do 0 in this case, that would be good enough, or I'll just do kind of negative 999. Our right boundary is next. Well, that's right here, that's 95. Our mean is still 110, standard deviation is 8. And when I do that, I get 0.0304. Okay? Now sometimes actually these problems get a little, what if I said I wanted the probability that there's someone between 100 pounds and 120 pounds. Because again, these numbers have to do with weights. Well, here we actually have a left and a right. So we're looking for is 100 pounds is about here, 120 pounds is about here. We're looking for this area right here. So we would say normal CDF, 100, 120, 110, 8. That's a pretty big area. What's going on? Oh, gee, that's weird. What's going on? Okay, not quite sure what happened there, but we get 0.7887, which is a pretty big area, right? It's a pretty big chunk. Okay, the next thing we want to talk about is sometimes the problems are phrased a little bit differently. So let me draw this curve, hopefully one last time. Probably not. Okay, boom, there's 110. And by the way, the pictures are really useful to kind of think about these kind of problems. What if I asked you a question that was, a student weighs student's weight, is the 40th percentile. How much does he weigh? Well, if you think about that question, it's a little bit different, because what we're basically saying is there's some student, here he is, we don't know how much he weighs, but we know that this area is 0.4. Little different question. Normal CDF tells us what this area is when we know the numbers on the x-axis, but here we don't know the number on the x-axis, we just know the area. There's a different calculator function that tells us this, and it's inverse norm. And the way inverse norm works is you give it a percentile. A percentile we always mean from the left, and then a mean and a standard deviation. So this particular problem we would do, change my color here, we would do inverse norm. The percentile is 0.4. Maybe percentile is not exactly the right thing, because this will always be a number less than 1. 110, 8. That's the mean, that's the standard deviation. And that tells us that the weight, which is 107.97 pounds. Now, sometimes these inverse norm questions can get a little bit tricky, because you have to rephrase them a little bit. So let's think about this. Okay? So we said here's mean of 110, sigma equals 8. What if I said the question was something like this? Only 3% of students weigh more than Bobby. And the question is, how much does Bobby weigh? How much does he weigh? Well, so what we're basically saying is somewhere, here's Bobby's weight, I'll call that X, and this area right here we know is 3% or 0.03. So you'd think we want to just use inverse norm with 0.03, but again, the way inverse norm works, it's always the percentile or from the left. So what percent of people weigh less than Bobby? Well, clearly the answer is 97%. So here you would do inverse norm of 0.97, again a percentile expresses a number less than 1, 110, 8, which gives us Bobby's weight is 125.05 pounds. Just one little quick observation about both inverse norm and normal CDF. The calculator knows the way the normal curves work. There is a way to do it kind of the more old-fashioned way, which is there's a table in the back of their book, but I won't mention that here as much. We'll briefly touch on it in class. But for any problem that you can't use the 68, 95, 99.7 rule, in class we will use inverse norm and inverse norm's friend, normal CDF.